A pair of stars circles an empty point in space, neither one truly holding the center, both leaning around an invisible balance between them. Around that slow-turning light, a planet waits in darkness, then watches two suns rise at once. Their shadows do not fall together. Their warmth does not arrive in one simple rhythm. Nothing here is still. Nothing belongs to only one path. If this quiet journey through strange orbits and distant worlds helps the night feel a little softer, consider subscribing, leaving a like, or sharing it with someone who enjoys falling asleep beside the universe. Somewhere, this video may be playing in a dark room, through small speakers beside a bed, or through headphones while the rest of the house has gone silent. Wherever it has found its listener, and whatever hour is glowing on the clock, this is a good place to let the room grow dim. The lights can fade, the body can settle, the sound can become part of the background, steady enough to follow, gentle enough to drift away from. Ahead are worlds that move in ways the solar system first seems to hide from view. Planets beneath several suns, a dark moon caught far from where it was born, a ring too thin to see, a cloud so distant no telescope has yet touched it with light, and a tilted blue planet rolling slowly through its long seasons. Each one is not a break in the order of space, but a quieter kind of order, shaped by gravity over ages too long to feel directly. The first step is small, before the captured moons, before the unseen cloud, before the planet tipped on its side. There is only motion around a shared center and the soft pull of bodies that never quite travel alone. Before any planet can be imagined beneath several suns, before a moon can be seen moving the wrong way around Saturn, before the outer edge of the solar system fades into a cloud no telescope has yet photographed, there is a quieter fact underneath all of it. Nothing in space truly orbits alone. Not even a single moon circling a planet. Not even a planet circling one calm star. Every object pulls on every other object. And every orbit is a shared motion, however uneven that sharing may be. The larger body may seem still. The smaller body may seem to do all the traveling. But gravity does not work that way. It always makes a pair. In the simplest picture of the solar system, the sun sits at the center, and the planets move around it in clean, silent paths. That picture is useful. It is also incomplete. The sun is vast compared with Earth, Mars, Saturn, or even Jupiter, and so the center of the solar system lies very close to the sun most of the time. Yet close is not the same as exact. The planets pull back. Jupiter pulls hardest of all. The giant planet contains more mass than all the other planets combined, and as it travels through its 12-year path around the sun, it draws the sun slightly away from the place where a simple drawing would put it. The sun does not remain perfectly fixed. It makes a small, slow motion of its own around a shared center of mass, a point determined by the balance of gravity between bodies. That center of mass is sometimes called a barycenter. The word sounds technical, but the idea is plain. When two objects are connected by gravity, they both move around a balance point. If one object is enormously heavier, that balance point lies deep inside the heavier object, and the lighter one appears to orbit it. If the two objects are closer in mass, the balance point moves outward, sometimes into empty space between them. The orbit then begins to look less like one body circling another and more like two bodies turning together around an invisible hinge. Pluto and Charon show this better than almost anywhere else in the familiar solar system. Pluto is larger, but Charon is not a tiny moon in comparison. It is big enough and massive enough that the shared center of mass between them does not sit inside Pluto. It lies outside Pluto's surface, in open space. From far away, the pair looks like two icy worlds turning around a point neither of them occupies. There is no hidden object there. There is no dark star, no dense stone, no unseen planet holding them in place. There is only balance. Pluto pulls on Charon, and Charon pulls on Pluto, and both obey the same quiet rule. This is where the clean picture of orbits begins to soften. Space is not built from still centers and obedient circles. It is built from relationships. A moon changes the planet it orbits. A planet changes the star it follows. A star with another star nearby cannot pretend to be alone. Each body leaves a mark on the motion of the others, sometimes so small that only careful measurement can reveal it, sometimes so large that the entire system becomes a slow dance around an empty point. The emptiness matters. In many systems, the most important place is not occupied by anything at all. It is simply where gravity balances. Around that point, stars turn. Around that point, planets may travel. Around that point, entire families of worlds can find a rhythm that lasts for billions of years. Binary stars make this visible on a grander scale. Instead of one star shining at the center of a planetary system, there are two. They may be nearly equal, each circling the shared center with a similar sweep, their light rising and falling as they move. Or one may be much heavier than the other, so the larger star drifts in a smaller path, while the smaller one traces a wider loop around the same balance point. The motion can be slow and stately, taking years or centuries. It can also be close and fast, with two stars turning around each other so tightly that their light blends into one point from far away. From Earth, many binary stars cannot be separated with the naked eye. They look like a single star, one small flame in the night. Sirius, the brightest star in the sky, carries a faint white dwarf companion. Alpha Centauri appears as one of the nearest stellar neighbors, but it is not a solitary sun. Polaris, used for centuries as a guide toward north, also belongs to a multiple system. The sky gives the impression of single lights. Deeper observation reveals partnerships. For a long time, that led to a tempting idea. Perhaps the sun was unusual because it was alone. Perhaps most stars were born with companions, while the solar system happened to form around one isolated star. The brightest stars supported that impression because bright stars are easier to see and because massive stars are more often found with companions. But the galaxy is not made mostly of bright blue and white stars. It is filled, overwhelmingly, with red dwarfs. Small, dim, long-lived stars that burn quietly for timescales far beyond the present age of the universe. Most of them are too faint to see without instruments. Many of them appear to live alone. That changes the feeling of the night sky. The stars most easily noticed are not always the most typical. Brightness can mislead. A pair of stars gives more light than one. Massive stars shine so strongly that they stand out across great distances. And massive stars are also more likely to form in crowded, turbulent nurseries, where companions are common. The quiet majority remains hidden in the background. Small red stars, faint and steady, many without close stellar partners. The sun is not as strange as it once seemed. It is not entirely ordinary either. It sits somewhere between the crowded brilliance of massive star systems and the dim solitude of red dwarf worlds. The birth of a star begins inside a cold cloud of gas and dust. A region of the cloud becomes denser. Gravity gathers it inward. The material falls, spins, flattens, and heats. At the center, a young star forms. Around it, a disk of leftover material may become planets, moons, asteroids, and icy bodies. In a calm enough place, the result can be something like the solar system. One star, several planets, and smaller debris spread through belts and distant reservoirs. But a cloud does not always collapse into one center. It can fragment. Several dense knots may form near one another, each gathering material, each becoming a young star. At first, the scene is not clean. Newborn stars pass close. Gas drags at their motions. Some are thrown outward, some pair off, some remain bound in layered arrangements, where a close pair acts almost like one object to a more distant companion. Stability is not given at birth. It is something the system settles into after the early chaos has removed what cannot remain. That is why multiple star systems often have a hierarchy. Two close stars orbit each other. Farther away, a third star orbits the pair. If there are 4 stars, there may be 2 pairs, each pair turning internally while both pairs circle a wider center. The pattern can keep building, though not without limit. Each level must be wide enough compared with the level below it. If the distances are too similar, the stars disturb one another too strongly. Orbits cross, energy shifts between bodies. One star may be pushed into a wider and wider path until it leaves the system completely. A stable multiple star system is not a crowd moving at random. It is more like nested motion. Small orbits inside larger orbits, close pairs inside wider pairs, balance points inside other balance points. To a distant observer, a tight binary can behave almost like a single star because the details of the pair blur together at large distance. To a planet close enough to one member of the pair, however, the difference may fill the sky. There are 2 broad ways a planet can survive near a binary star. It can orbit one star while the other stays far enough away to act as a distant companion. Astronomers call this an S-type orbit, though the name matters less than the shape. The planet belongs mainly to one sun. The second sun rises and sets as a bright visitor, sometimes stronger, sometimes weaker, depending on its long path around the primary star. If the distance is wide and the orbit stable, the planet may continue for ages, warmed mostly by one star, while the other marks the sky in a slower cycle. The other arrangement is stranger to imagine but real. A planet can orbit both stars together. It stays far enough away that the 2 stars, though separate, act gravitationally like a central pair. The planet does not choose one sun. It circles the shared center around both of them. This is called a circumbinary orbit. From such a world, day and night would not follow the simple pattern known on Earth. 2 stars would move across the sky, sometimes close together, sometimes apart. Their eclipses might dim the light for a time. Their changing positions would make the seasons less like a clean tilt and orbit rhythm and more like a layered pattern of warmth. The first confirmed example of such a world around 2 ordinary stars gave the idea a firmer shape. Kepler 16b orbits a pair of stars, one smaller and cooler than the Sun, the other smaller still. The planet is cold and probably gaseous, not a place with an Earth-like surface. Yet its existence matters because it shows that planet formation can survive around 2 suns. The protoplanetary disk around a binary system is stirred and shaped by the motion of both stars, but it can still gather material into a planet. Not in every case, not easily, but often enough that such worlds are no longer only imagined. A later discovery by TESS, TEI 1338b, added another quiet confirmation. It too circles 2 stars. It crosses in front of them from the telescope's point of view, causing dips in their light that reveal the planet's presence. The method depends on patience, waiting for a tiny shadow, measuring how much light disappears, and working out the shape of an unseen orbit from the rhythm of dimming. A planet around 2 stars does not produce a perfectly simple signal. The stars move, the planet moves, and the geometry changes. Still, the shadow returns. The world is there. These discoveries shift the meaning of a binary star. A pair of suns is not automatically hostile to planets. It is more complicated, but not forbidden. Gravity, when arranged with enough distance and rhythm, can protect as well as disturb. A planet too close to the shifting pull of two stars may be thrown into chaos. Farther out, there can be a zone where the pulls blend into a stable path. Within that region, worlds may circle for long spans of time, receiving light from two moving sources and carrying shadows that never quite repeat in the same way. The same principle can scale upward into systems with 3 stars, 4 stars, or more. A planet in such a system does not need to feel the full disorder of every star at once. If the stars are arranged hierarchically, the closest gravitational relationship dominates. A planet may orbit one star, while a distant binary appears only as a bright pair in the sky. Another planet may orbit a close binary, while a third star travels far outside. Still farther away, a planet might circle an entire group, seeing several suns not as blazing disks but as bright points that change slowly over years or centuries. The phrase, "several suns," can sound dramatic, but the actual sky of such a planet would depend on distance. A world orbiting the outer edge of a 7-star hierarchy might technically belong to all 7, yet most of the light could be weak. The stars may gather into 2 distant clumps, like bright knots separated in the sky. They might not warm the planet much at all. The world could be cold, moving through a wide orbit where the stars look less like suns and more like a small constellation that belongs only to that system. Closer in, the scene changes. A planet orbiting one member of a triple system might have one true daytime star, large and steady enough to shape weather and climate. The other 2 stars might rise together as a pair, brighter than planets, dimmer than the main sun, shifting over a longer cycle. Night would not always be dark in the same way. Sometimes the companion stars might hang above the horizon, giving the landscape a faint second light. Sometimes they might disappear behind the main star's glare. The sky would keep time in more than one rhythm. The stability of such planets depends on boundaries. Too close to a companion star, the orbit becomes vulnerable. Too far from the host star, the planet may be pulled into the wider system or slowly disturbed over time. Astronomers use models to map these regions, looking for paths where small gravitational nudges do not grow into disaster. A stable orbit is not one without disturbance. It is one where the disturbances repeat, average out, or remain small enough for the planet to stay bound. This is true even in the solar system, where the arrangement looks simple at first. Earth's path is not a perfect circle. The moon pulls on Earth. Jupiter tugs on asteroids. Neptune shapes the Kuiper belt. The sun itself moves around the solar system barycenter as the planets draw it slightly from side to side. The whole structure remains stable not because nothing disturbs it, but because the disturbances are part of its long pattern. There is comfort in that. Order in space does not require stillness. It requires a rhythm that can survive change. For planets in multiple star systems, light becomes part of that rhythm. On a circumbinary world, the 2 stars may eclipse each other, turning full daylight into something briefly softer. Their combined brightness may rise and fall as they move. If one star is cooler and redder, while the other is hotter and whiter, the color of daylight itself may shift by a small amount, giving the sky a slow pulse of tone. Shadows may split and merge. A rock on the ground could cast 2 dark shapes in the morning and one blurred shape later in the day. Not because the ground has changed, but because the suns have. Climate would depend on more than distance from a single star. A planet's orbit around 2 suns may carry it through zones of slightly changing energy. If the orbit is stable and the stars are not too variable, the world might still maintain a steady average temperature. If the orbit is more stretched, seasons could be driven not only by axial tilt, but also by changing distance from the binary pair. The planet would not need chaos to be unusual. It would only need 2 clocks in the sky instead of 1. Formation is the deeper question. A planet grows from small grains that collide, stick, break, and collide again inside a disk of gas and dust. Around one young star, the disk has a central source of gravity. Around 2, the center itself moves. The binary clears a cavity near the middle, stirring the inner disk and making some regions too unstable for planets to gather. Yet beyond that disturbed zone, material can settle into safer paths. Dust grains can become pebbles. Pebbles can become planetesimals. Planetesimals can become cores. The process does not stop because there are 2 stars. It changes shape. Some planets in binary systems may also arrive later. A world might form around one star and be pushed outward. A planet might be scattered, captured, or shifted by interactions with other planets. The final architecture of a system is not always the same as its birth arrangement. That is another lesson repeated throughout astronomy. Objects travel, orbits migrate. Bodies that seem out of place often carry memories of earlier violence, softened by time into a stable present. The idea will return when a dark moon is found moving backward around Saturn. It will return again at the edge of the solar system, where icy bodies wait in orbits so wide that the sun becomes only the strongest nearby star rather than an overwhelming master. But the first version of the lesson is already here, in the motion of 2 stars around an empty point, and in the possibility of a planet moving calmly around them both. A binary sunset is not only an image from fiction. Somewhere in the galaxy, real planets move under double light. Some are gas giants. Some may be icy. Some may have no surface at all, only layers of atmosphere deepening under pressure. Others, still unknown, may be smaller and darker, too faint or too distant for current instruments to measure clearly. Their skies would not be copies of Earth's sky. Their years would not be Earth's year. Yet their motion would obey the same rule that holds the Moon, Pluto, Jupiter, and the Sun itself. Gravity does not ask for simplicity, it asks for balance. A single star can hold planets. 2 stars can hold planets. Several stars, arranged with enough space between their inner and outer motions, can also become a home for worlds. The result may look strange from the surface. It may place more than one sun in the sky. It may stretch night into a pattern of dim companion light and shifting shadows. But underneath the strangeness is the same quiet geometry, bodies falling forever around a center they never reach. From a great distance, such a system may shrink into a single point of light. The binary motion disappears. The planets vanish. The nested orbits become too small to see. Only the star, or what looks like one star, remains. Then the telescope watches carefully. The light dips. The spectrum shifts. A hidden companion pulls. A planet crosses the face of a sun, then another. The point of light begins to unfold into structure. That unfolding is one of astronomy's gentlest surprises. The universe often hides complexity inside apparent simplicity. One star becomes 2. A steady orbit becomes a shared balance. A planet that should have been impossible leaves a measurable shadow, and beyond that shadow, there may be a sky where 2 suns cross slowly above the horizon, where each day is held between more than one source of light, and where the ground, if there is ground, turns through a pattern no human calendar was made to follow. The motion continues without hurry. Stars circle their centers of mass. Planets keep to the safe parts of their paths. Light travels outward, carrying the evidence across years and centuries until a telescope receives a fraction of it. In that faint signal, the old simple picture changes. The center is not always occupied. The brightest object is not always still. The most stable systems are not always the least complicated, and somewhere in the dark, around a point where nothing can be seen, 2 stars keep turning. The first planet under several suns does not need to look strange from far away. To a telescope, it may be only a pattern in light, a small dimming that returns after a measured span of time, a trace crossing the face of one star and then passing near the other. The world itself is hidden. Its clouds, if it has clouds, cannot be seen. Its color cannot be known with certainty. Yet the motion gives it away. Something dark is moving where only starlight should be. A circumbinary planet lives outside a pair of stars. The two stars turn around their shared center, and the planet circles both of them from a safer distance, far enough away that the shifting pull of the pair becomes one wider rhythm. Close to the stars, the gravity is too restless. The path of a planet would be bent first one way, then another, until the orbit no longer held, farther out. The two stars become a combined source of gravity. Their separate motions still matter, but they do not tear the planet loose. They become part of its year. The sky from such a world would not follow the plain pattern of one sunrise and one sunset. If the planet had a surface, and if it rotated under the light, day could begin with one star climbing before the other. A smaller, redder sun might rise first, staining the horizon with a low copper glow. Later, a brighter star might follow, sharpening the shadows and changing the color of the ground. At some times, the two stars would stand close together, and the daylight would seem almost ordinary. At other times, they would spread apart, and every stone, ridge, or frozen plain might carry two shadows angled away from each other. Kepler 16b gave this idea its first firm place in modern astronomy. It is not an Earth-like planet. It is most likely a cold giant, roughly Saturn-sized, moving around two stars that are both smaller than the Sun. One star gives most of the light, the other is dimmer, cooler, and much less massive. Together they form a tight binary, a pair close enough that their mutual orbit shapes everything around them. The planet travels outside them, in a path that remains stable because it keeps its distance from the strongest confusion near the center. The discovery did not come from seeing the planet as a disk. It came from watching light fall away. The Kepler Space Telescope stared at the same region of sky for years, measuring the brightness of stars with a steadiness impossible for the human eye. When a planet crosses in front of a star, the star's light dips by a tiny amount. Around one star, this dip can repeat in a simple rhythm. Around two stars, the rhythm becomes more complicated. The stars are moving around each other. The planet is moving around both. Sometimes the geometry lines up. Sometimes it does not. The signal is not a clean metronome. It is a slow pattern that has to be followed over time. That unevenness is part of what made the discovery so important. The planet was not only circling two stars, it was doing so in a system where the stars also eclipsed one another, passing in front of each other from Earth's point of view. The light curve, that thin record of brightening and dimming, carried more than one kind of shadow. First one star dimmed the other. Then the planet dimmed a star. The timing changed because everybody was in motion. From those shifts, astronomers could rebuild the hidden architecture of the system, not by looking at it directly, but by listening to its brightness. There is a quiet beauty in that method. A distant world leaves no picture, only a pause in light. The pause is small. It may last only a few hours, yet within it lies the size of the planet, the angle of its orbit, the shape of the binary pair, and the fact that a planet can form where older assumptions once expected too much disorder. The shadow is enough. Before such discoveries, planets around binary stars were not impossible in theory, but they felt difficult. A young binary system shapes its surrounding disk of gas and dust. The two stars carve a hollow region near the middle, clearing material from the inner zone and stirring what remains. Dust grains near the center may collide too fast to stick. Small bodies may be scattered before they can grow. In the early life of the system, the environment is not gentle. It is a place of shifting gravity, waves through the disk, and material forced into rings, spirals, and crowded edges. Yet planet formation does not require perfect calm. It requires enough time, enough material, and enough regions where collisions can become growth instead of destruction. Outside the cleared central cavity, dust can settle into safer lanes. Grains become pebbles. Pebbles become larger bodies. Gravity begins to help the growing pieces gather more mass. The binary still tugs at the disk, but farther out, the tugs can become a repeating pattern rather than a breaking one. In that space, planets can emerge. Some circumbinary planets appear close to the inner edge of stability, just beyond the region where the binary would throw them into unsafe paths. That is a clue. It suggests that planets may form farther out, and then migrate inward through the disk until they reach a boundary where the binary's gravity stops them from moving much closer. The result is a world parked near the edge of chaos, not inside it, but close enough that the shape of the binary still governs its year. TOI 1338b added a second kind of softness to the story. It was found by TESS, another telescope watching for dimmings in starlight. The system contains two stars, and the planet moves around both, much like Kepler-16b in the broad sense. Though each system has its own details, the discovery was made through the patience of transit timing again. Tiny changes, small shadows, repeated measurements. The planet itself remains unseen as a world, but its presence is written into the light of its suns. These worlds are not rare decorations added to astronomy. They change the estimate of what kinds of planetary systems the galaxy may hold. Binary stars are common, especially among stars more massive than the Sun. If planets can form around a meaningful fraction of them, then the number of possible planetary architectures grows wider. A galaxy of single-star solar systems becomes something more varied. Planets around one star with a second sun in the distance, planets around two stars together, planets in triple systems where one pair burns close and a third star moves far away. A planet orbiting one star in a wide binary would have a different experience. It may receive nearly all its warmth from its primary star, while the second star remains a bright companion in the sky. The second star could take years, centuries, or longer to move through its wide orbit. From the planet's surface, it might appear as an unusually bright point, sometimes visible in the day, sometimes ruling the night. It would not necessarily create two full suns. Distance matters. A companion star can be gravitationally important over long spans while still being too far away to warm the planet much. That kind of system may be easier for planets. If the companion star stays distant, the disk around the main star can behave more like a single-star disk, at least in its inner regions. Planets may gather close to the primary star, while the companion shapes the outer edges. The second star may disturb distant comets, tilt debris belts, or slowly alter the paths of outer planets. Its touch is not constant like sunlight. It is slow gravity, working over long intervals. The same distinction matters when imagining several suns. A planet can belong to a multiple star system without having several large suns overhead. In a hierarchical system, a close pair of stars may sit at one level, while another star circles far outside, and a planet may orbit only one member of the structure. To the planet, the nearest star is the true sun. The others are part of the wider environment, bright markers of the system's deeper architecture. They may rise as stars, not suns, unless the planet's path places it near enough to receive their light strongly. In a triple system, the possible skies multiply. A planet around one star could see the other two as a pair of distant lights. A planet around a close binary could see a third star wandering slowly through the background, changing its position from year to year. A planet around all three would need to travel far enough out that the inner motions blur together into a central mass. Its year could be long, its sunlight could be weaker. The stars might appear clustered, not spread across the sky, depending on the shape of the system. The largest multiple systems make the idea even more delicate. A 7-star system can be stable only if it is layered. 2 stars close together, another pair far away. A single star bound to one pair, a wider orbit around all of them. A planet at the outer level might technically orbit every star in the system, but the word sun would become less simple. Some of those stars might be little more than bright beads in the sky. The planet would count them as part of its gravitational family, while its surface, if it had one, might remain dim and cold. The habit of counting suns can mislead. Light and gravity do not fade in the same way in ordinary imagination, though both weaken with distance. A star twice as far away gives only a quarter of the light. A star 10 times farther gives 1/100th. A distant companion can still shape orbits over time while barely touching the planet's temperature. The sky may be rich with stellar companions, yet the climate may depend on one nearby star or on the combined glow of a close pair. Where light does matter, the effects can be subtle and strange. On a circumbinary planet, there may be times when one star passes in front of the other, as seen from the planet. The total daylight would fall, not to darkness, but to a softer level. The color of the sky could change slightly if the blocked star is hotter or cooler than the one remaining visible. The event would not be an ordinary eclipse caused by a moon. It would be the suns eclipsing one another, the whole day breathing down for a short while before brightening again. The calendar would also be different. On Earth, the year is the time it takes to orbit one star, and the seasons arise mainly from the tilt of the planet's axis, around 2 stars. There are more cycles layered together. The binary has its own period. The planet has its longer orbit. The stars' separation in the sky changes as they circle. If the planet's orbit is slightly stretched, the distance to the pair also changes. A climate system under those conditions would not need to be violent to be complex. It would receive a slow pattern of energy with more than one beat. Habitability around binary stars is therefore not a simple yes or no. A planet must remain in a stable orbit. It must receive an amount of stellar energy that allows suitable temperatures if other conditions are right. Its atmosphere, rotation, water inventory, magnetic environment, and history all matter. The presence of 2 suns does not automatically prevent these things, it only adds more conditions. Some binary systems would be too tight, too unstable, too bright, too variable. Others may allow calm zones where a planet could keep a steady average climate for long periods. There is no need to make such worlds more dramatic than they are. Their reality is enough. A planet may move under 2 stars and still spend most of its existence in quiet repetition. Dawn follows night. Shadows shift. Clouds, if present, respond to warmth. Ice, if present, melts or hardens according to the same physics known everywhere. The sky is unusual, but the laws are not. One reason these planets feel so compelling is that they reveal how flexible planetary systems can be. The solar system gives one arrangement, one star, inner rocky planets, outer giants, belts of debris, distant icy bodies. It is a useful example, but not a template that every system must follow. Around other stars, astronomers have found hot giant planets pressed close to their suns, compact systems of several worlds inside Mercury's orbit, planets around red dwarfs, planets in resonances, planets with years lasting only days, and planets in binary systems where daylight comes from more than one source. The galaxy does not seem interested in repeating one design. It keeps the laws and changes the architecture. For a sleep documentary, that variety can be held gently. There is no need to rush from one discovery to another. The important feeling is slower. Each new orbit softens the old assumption that a planetary system must look like home. Home is one version. Kepler 16b is another. TOI 1338b is another. A planet around one star in a wide binary is another still. The possible arrangements fan outward, not as fantasy, but as measured consequences of gravity acting in different settings. Detection remains difficult. A circumbinary planet may not transit every orbit from Earth's point of view, because the stars are moving and the planet's path is not aligned in the same simple way each time. The dips in light can vary. Some transits may be missed. Some systems may hide their planets entirely if the alignment is wrong. Other methods, such as measuring the wobble of stars or timing variations in eclipsing binaries, can also reveal companions. But each method has limits. The catalogue of known circumbinary planets is therefore not a complete census. It is a window. Beyond that window, many systems remain unresolved points of light. A star that looks single may be two. A planet's signal may be tangled with stellar motion. A companion star may be too dim or too close to separate. Instruments improve, and the points begin to divide. Spectra show hidden shifts. Light curves show repeated shadows. Direct imaging reveals distant companions. What seemed simple becomes layered. The same process has happened many times in astronomy. Saturn was once a strange planet with handles before its rings were understood. The Milky Way was once the whole universe before other galaxies were measured. Stars once looked fixed before their proper motions were recorded. A single light in the sky becomes a system. A system becomes a history. A history becomes a clue to how matter organizes itself across time. Multiple star planets belong to that pattern. They are not exceptions that break astronomy. They are reminders that gravity can build stable order from arrangements that look, at first, too complicated. The motion is not random. The binary pair clears a space. The disk adjusts. The planet finds a safer path. The years begin. Somewhere, a cold giant is circling two small stars. Somewhere else, a planet moves around one sun while a second burns far away, bright enough to mark the night but not enough to warm the ground. Farther still, there may be planets in triple or quadruple systems, carrying skies where companion stars drift with slow patience. None of these worlds need to be imagined as noisy or chaotic. Most of their time is silence. Most of their motion is repetition. That repetition is what allows them to exist. Orbit after orbit, the planet returns. The stars have shifted, but not too much. The gravitational tugs arrive in a pattern the planet can survive. Light falls from two directions. Shadows cross and separate. The system breathes in cycles longer than weather, longer than seasons, sometimes longer than civilizations could easily keep track of. At the center, there may be no object at all, only a point of balance. Around it, two stars continue their measured turn, and beyond them a planet follows the wider curve, held not by stillness, but by the lasting agreement of motion. Far from the bright rings of Saturn, beyond the familiar paths of Titan and Enceladus, a dark moon moves through a colder part of the planet's domain. It does not share the calm order of Saturn's inner moons. It does not travel with the main current. It circles in the opposite direction, far away from the flat plane, where most of Saturn's family appears to belong. In the dim outer region, where the planet is only a hard, pale light, and the rings would not fill the sky, Phoebe keeps its long backward path. Seen from a distance, Phoebe is small. It is only a little more than 200 kilometers across, a rough sphere with a surface dark enough to drink in most of the sunlight that reaches it. It is not smooth. It is not young. Craters cover it so heavily that the moon seems to have kept the memory of nearly every impact that ever touched it. Bright ice shows through in places where the dark upper coating has slipped away, leaving pale scars across crater walls and slopes. The surface looks old in the way some objects in space look old, not by wrinkles, but by silence, darkness, and damage that has not been erased. Saturn's inner moons move mostly in the same direction as the planet rotates. They follow paths that make sense if they formed from a disk of material around young Saturn, much as planets formed from the disk around the young Sun. Phoebe does not fit that pattern. Its orbit is retrograde, meaning it moves the opposite way around Saturn compared with the regular moons. That backward motion is more than a strange detail. It is a sign of origin. A moon born in Saturn's original disk would almost certainly share the direction of that disk. Phoebe's path points somewhere else. The moon is a captured body. It did not grow quietly beside Saturn's other regular moons. It formed in a colder region of the outer solar system and later entered Saturn's control. The capture itself is not directly recorded. There is no image of the moment. There is only the orbit, the chemistry, the density, and the shape of the moon today. Together, they tell a story without needing to speak loudly. The discovery began far from Saturn, on photographic plates. In the late 19th century, astronomers were learning to let cameras gather light for longer than the eye could manage. A faint object, too dim for ordinary sight, could leave a mark if the exposure lasted long enough. At the Harvard College Observatory's southern station in Peru, plates of the sky were made under clear, high air and sent back for careful inspection. Human computers examined them with magnifying lenses, looking for small changes among the fixed points of stars. In those plates, William Henry Pickering found a speck moving with Saturn. It was faint, much fainter than anything visible without a telescope, but it shifted from plate to plate in a way that showed it belonged to the planet's system. In 1899, Phoebe was announced. It became the first natural satellite discovered by photography rather than by direct visual observation through a telescope. That detail gives the moon a fitting beginning. Phoebe was not an obvious object. It entered astronomy through patient light collected on glass. For much of the next century, patience was still all that astronomy had. Phoebe was known, tracked, measured, and recognized as unusual, but it remained small and remote. Its distance from Saturn made it hard to study. It travels at a mean distance of almost 13 million kilometers from the planet, far beyond the orbit of Iapetus, and much farther still than the bright inner moons. One journey around Saturn takes about 550 Earth days. It is a moon with a long year, moving in a wide, cold loop, where the planet's pull is still strong enough to hold it, but weak enough to make the connection feel stretched. Voyager 2 passed through the Saturn system in 1981, but Phoebe was too far from the spacecraft's path for a close view. It appeared as a dark, irregular form, enough to confirm its rough character, not enough to reveal the world it was. The moon remained a question waiting at the edge of Saturn's influence. Cassini changed that, but only once. When the spacecraft approached Saturn in 2004, mission planners saw that its arrival path could bring it near Phoebe before the main engine burn that would place Cassini into orbit around Saturn. After that burn, the spacecraft would be bound to the inner system. It would not have the fuel to return to the far outer moon. The encounter had to happen before Saturn fully took Cassini in, so Cassini came in from the dark. On the 11th of June, 2004, 19 days before orbital insertion, the spacecraft swept past Phoebe. The relative speed was high. The window was short. For a few hours, the moon changed from a distant speck into a landscape. Cameras and spectrometers worked quickly, gathering the only close view humanity has ever had of that captured body. Then Cassini moved on toward Saturn, and Phoebe receded again. The images did not show a simple icy moon. They showed a battered object, dark on top, pale beneath, with craters nested inside older craters and slopes marked by landslides. The largest basin, Jason Crater, is about half the diameter of Phoebe itself. An impact large enough to make such a wound could have broken a weaker object apart. Phoebe survived. That survival suggests a body with internal strength, not merely a loose cluster of rubble barely held together. Gravity on Phoebe is weak. A stone dropped from a hand would fall slowly, as if the surface were hesitant to receive it. Yet, even weak gravity can move material over time. When impacts shake crater walls, dark debris can slide downward, exposing brighter ice below. Cassini saw pale streaks and patches where the surface covering had given way. These markings matter because they show that the darkness is not the whole moon. It is a coating. Under it lies a brighter, icier body. The composition confirmed that impression. Cassini detected water ice on the surface, along with carbon dioxide, iron-bearing minerals, and dark primitive material rich in carbon. This mixture does not resemble the clean, bright ice of some inner moons. It feels more like the outer solar system, cold, chemically old, and only partly altered by sunlight. Carbon dioxide is especially useful as a clue because it is volatile. In warmer inner regions, it would not remain easily exposed over long times. On Phoebe, its presence points back toward colder origins. Density gives another clue. Phoebe is denser than many of Saturn's regular icy moons. Its average density suggests a substantial rocky component mixed with ice. It is not simply a ball of frozen water. It contains enough rock to resemble bodies from farther out. Objects that formed where ice and darker minerals gathered together in the early solar system. In that sense, Phoebe looks less like a native moon of Saturn and more like a surviving fragment from the region beyond the giant planets. That does not mean Phoebe came from the present Kuiper belt in a simple straight path. The early solar system did not keep its architecture fixed from the beginning. The giant planets likely shifted their orbits after formation. As they moved, they disturbed wide reservoirs of icy bodies. Some were thrown inward, some were sent outward, some escaped the sun altogether. Some were caught by planets and became irregular moons, living far from the regular satellite systems with tilted, stretched, or backward orbits. Phoebe belongs to that irregular family. Around the giant planets, irregular moons often travel far away, at high inclinations, and sometimes in retrograde motion. They are not the round, orderly moons that formed in flat disks close to their planets. They are captured remnants, small bodies whose paths were rewritten by gravity. Their surfaces can preserve material older than the present arrangement of the planets. Each one is a clue to a time when the solar system was not settled. Capture is not simple. A planet cannot usually grab a passing object by gravity alone unless energy is removed from the object's motion. Without that loss of energy, the body approaches, curves around, and leaves again. In the early solar system, there were several ways to make capture possible. A body might pass through gas around a young planet and slow slightly. It might interact with another moon or another small body, giving away enough energy to become bound. It might be captured during the larger reshuffling of planetary orbits, when close encounters were more common and the boundaries between regions were less calm. The exact path that brought Phoebe to Saturn is not known. The honest answer is that the broad outline is clearer than the details. Its backward distant orbit shows capture. Its composition suggests an outer solar system origin. Its density and surface chemistry point to a primitive, icy rocky body. The precise route, the timing, and the encounter that made Saturn its permanent host remain hidden inside the early history of the planets. Phoebe's present orbit is wide and lonely, but it is not meaningless. Its distance helps explain why it remained so different from the inner moons. Close to Saturn, tidal forces can flex moons, warm interiors, shape orbits, and drive geological change. Enceladus, much nearer in, is a world of active plumes and hidden ocean chemistry. Titan carries a thick atmosphere and methane weather. Phoebe, far outside, receives little of that intimate influence. It is held by Saturn, but not remade by Saturn in the same way. That distance also changes the sky from Phoebe. Saturn would not tower as it does from nearby moons. It would be a bright object, much larger than a star, but far smaller than the overwhelming planets seen from inner orbits. The rings, so wide and famous from Earth's images, would be too thin and distant to dominate the view. From Phoebe's surface, the scene would be darker, quieter, more spare. The sun would be weak. Saturn would shine in the distance. The rest would be black sky and slow motion. There is no air to soften the light. No wind moves dust into dunes. No liquid cuts valleys. The surface changes by impact, by sliding debris, by the slow darkening of exposed material under radiation and micrometeoroid bombardment. On such a body, time does not flow through weather. It accumulates in craters. The craters themselves are records of exposure. A young surface may hide its age through resurfacing, lava, ice flows, tectonic motion, atmosphere, erosion. Phoebe has little of that. Impacts remain. Newer craters cut older ones. Small craters pepper larger basins. The surface becomes crowded with evidence until it reaches saturation, a state where new impacts begin to erase old impacts as often as they add new marks. That kind of surface suggests great age, a long span of being struck in open space. The bright material exposed by landslides gives the moon a layered appearance. A dark mantle only a limited depth, thick, may cover an icier interior. That mantle could come from the moon's own surface changing under space weathering, or from material deposited and mixed over time. It does not have to be thick to control the appearance. A thin, dark skin is enough to make an icy body look almost black from a distance. This contrast between surface and interior is one of Phoebe's most useful lessons. Objects in space do not always show what they are at first glance. A dark moon can be rich in ice. A small body can preserve chemistry from far beyond its present orbit. A backward path can carry a memory of capture. The visible surface is only the first layer of evidence. Phoebe may even have begun to differentiate, separating heavier, rocky material toward its center and lighter ice outward. It is too small today to be a planet, and it never became one. But its density and shape suggest it may be more than a simple leftover chunk. It could be a planetary embryo that started down a path toward internal structure and then stopped, frozen into an unfinished state. Such bodies are valuable because they show intermediate steps in the building of worlds. They are not planets, but they remember some of the same processes. In a calmer system, Phoebe might have remained in the outer solar system, one of many dark, icy bodies moving beyond Neptune. It might never have become a moon. It might have stayed anonymous, too faint and small for easy discovery. Saturn changed its role. By capturing Phoebe, the planet preserved it in a new setting, turning it into an accessible messenger from a distant region. Accessible does not mean close. It only means that one spacecraft, on one carefully arranged path, could finally pass near enough to read its surface. Cassini's flyby remains brief compared with the length of Phoebe's story. The spacecraft crossed the distance, took images, measured light, felt a tiny gravitational tug, and left. The moon continued. Its orbit did not change in any meaningful way. The encounter was a moment of attention in a history measured in billions of years. That contrast is gentle and strange. Human missions are fast, precise, full of planned seconds and narrow windows. Phoebe is slow. Its year around Saturn lasts longer than a year and a half on Earth. Its surface has waited through the migration of planets, the formation of Saturn's regular moons, the settling of the rings, the rise of life on Earth, and the building of instruments capable of finding it. Then, for a few hours, it filled a camera frame. The data from those hours still shapes how the moon is understood. The measured density came from how Phoebe's gravity altered Cassini's path by a tiny amount. Spectrometers separated reflected light into signs of minerals and ice. Images showed the landforms. None of these measurements alone tells the whole story. Together, they build a picture of a captured, ice-rich, rock-bearing object from the early outer solar system. Phoebe also changes the way Saturn's system is seen. It is tempting to imagine a planet's moons as a family formed in place, each one part of the planet's own birth environment. Saturn does have such moons. It also has outsiders. Its outer region holds small irregular satellites, objects that came from elsewhere and found long-term orbits around the planet. The system is not one story. It is several histories sharing the same gravity well. Phoebe is the largest of Saturn's irregular moons. That size makes it especially important. Smaller irregular moons may be fragments, collision products, or captured bodies too faint to study in detail. Phoebe is large enough for surface mapping, density measurement, and compositional study. It gives the irregular moon population a face, dark and scarred, but readable. The moon's backward orbit also prepares the next part of the journey. Phoebe does not only keep evidence on itself, it releases material. Tiny impacts strike its surface and lift dust into space. Because the moon is small and gravity is weak, some of that dust escapes. It does not fall back immediately. It enters orbit around Saturn, moving in the same broad retrograde direction as Phoebe. Over long spans, this escaping dust becomes more than a local haze. It becomes a wide and faint structure around the planet. That structure is almost impossible to imagine from the brightness of Saturn's main rings. The famous rings are flat, icy and bright, catching sunlight in a thin plane close to the planet. Phoebe's dust belongs to a different kind of ring. Enormous, tilted, dark, and spread so thin that it escaped detection until infrared instruments could sense its faint warmth. The captured moon, already a visitor from elsewhere, leaves a trace across millions of kilometers. For now, Phoebe continues its distant lap. It moves against the main flow, not in rebellion, but in memory. Its path keeps the signature of the encounter that trapped it. Its surface keeps the marks of the impacts that shaped it. Its chemistry keeps hints of the cold place where it formed. Around Saturn, among bright rings and active moons, Phoebe remains dark, quiet, and old. It is not out of place anymore. Time has made it part of the system. But it still carries the story of somewhere else. The dust from Phoebe does not leave as a storm. It leaves grain by grain, lifted by impacts too small to notice from far away. A tiny meteoroid strikes the dark surface. A little material is thrown upward. Some of it falls back in slow arcs under weak gravity. Some rises with just enough speed to escape the moon entirely. Once free, it does not vanish. It becomes part of Saturn's wider space. A faint inheritance from a captured moon that has been shedding itself for billions of years. Close to Saturn, the famous rings are bright and thin, a flat plane of ice, reflecting sunlight with a cold, clean shine. They are the rings every image remembers. They curve around the planet like a pale blade, divided by gaps and waves, shaped by moons that shepherd their edges and disturb their particles. Phoebe's ring is nothing like them. it is far outside. It is tilted. It is dark. It is so thinly spread that for a long time no telescope saw it at all. The ring made by Phoebe is not a narrow band that would gleam in a small telescope. It is a wide, diffuse cloud of dust, wrapped around Saturn at distances where the planet's ordinary rings would seem close to the center, almost like a separate system. Its particles are scattered through such a large volume that the structure is nearly empty by any everyday measure. A spacecraft could pass through it and not seem to pass through anything. There would be no wall of dust, no visible haze, no shining arch. Only space, black and quiet, with a few dark grains moving through it. That emptiness is part of why the ring remained hidden. Dust that, far from Saturn, receives weak sunlight. The grains are dark because they come from Phoebe's surface. And dark grains do not reflect much light back toward Earth. In visible light, the ring almost disappears. It is not absent. It is simply not giving the kind of signal that ordinary seeing prefers. To find it, astronomers had to look for warmth instead of brightness. The Spitzer Space Telescope did that in 2009. It observed the Saturn system in infrared light, where cold dust can reveal itself by the faint heat it emits. The ring appeared not as a bright feature but as a broad thermal glow, a quiet signal spread over a huge region around the planet. The discovery changed the scale of Saturn's ring system. The largest ring was not the bright icy disk seen beside the planet. It was a distant, dark halo made from dust released by a small backward moon. The size is difficult to hold in the mind, so it is better to picture Saturn first as a pale bead inside its main rings. Then the view pulls back. Titan's orbit passes inside the wider system. Iapetus travels much farther out, crossing the space where the outer moons keep slower company. Still the view pulls back. Phoebe moves in a distant, tilted path, and around that path lies the dust, spread across millions of kilometers. Saturn's familiar rings become a narrow, bright detail near the middle, while the Phoebe ring fills the darkness beyond them. The particles in the ring share Phoebe's general motion. They move around Saturn in a retrograde direction, opposite to the path of most of the major moons, and opposite to the bright main rings. This matters because direction in a planetary system is not only geometry, it decides how bodies meet. Two objects moving the same way may overtake one another gently. Two objects moving opposite ways collide with much greater relative speed. Phoebe's dust travels against the ordinary flow. Iapetus lies along that road. It is one of Saturn's stranger moons, large enough to be round, distant enough to move slowly, and divided in color so strongly that for centuries it puzzled astronomers. One side is bright, almost icy white. The other is dark, brown-black, as if the moon has been dipped into shadow. Giovanni Cassini noticed the difference in the 17th century because Iapetus appeared brighter on one side of its orbit than on the other. Sometimes it was easier to see. Sometimes it faded. The moon was turning one face forward along its path, and that forward face was dark. The Phoebe ring gave this old problem a natural source. Dust grains from Phoebe drift slowly inward towards Saturn. Iapetus, moving prograde, travels the other way around the planet compared with those grains. Its leading hemisphere, the side facing forward in its orbit, runs into the incoming dust. Over long spans of time, the dark material coats that face. The process is slow, too slow to watch happening in a human lifetime, but the result is written across the moon. Iapetus carries the color of another body. The image is simple and quiet. A distant moon shedding dark dust, and another moon sweeping through it like a stone moving through falling ash. The grains are tiny. The distances are enormous. The effect is patient. No single impact paints the surface. No brief event changes the moon at once. Instead, orbit after orbit, The leading side of Iapetus gathers what Phoebe has lost. This is not the whole story of Iapetus's two-tone surface. Once dark material begins to collect on one side, it absorbs more sunlight than the bright ice around it. The darker ground warms slightly more. Ice there can slowly migrate away, sublimating into vapor and then recondensing on colder, brighter regions. This makes the dark side darker and the bright side brighter. A small difference becomes stronger over time. Phoebe supplies the first dark coating. Thermal migration helps sharpen the contrast. That kind of feedback is common in planetary science. A surface is changed by one process, and the change allows another process to work more strongly. A patch of darker ground warms. Warmth moves ice. Lost ice exposes more dark material. The cycle continues. On Iapetus, the result is not a gentle gradient but a dramatic division, one hemisphere leading with darkness, the other keeping more of its pale, icy face. The dark coating also reveals the value of tiny particles. Dust can look unimportant because it is small. In space, small things can have large consequences when time is long enough. Micrometeoroids change airless surfaces. Fine grains darken ice. Charged dust moves through magnetic fields. Ring particles gather into bands, waves, and arcs. A few grains from Phoebe, multiplied by billions of years, become a planetary scale mark. Phoebe itself is not being destroyed quickly. The dust production is slow, and the moon remains intact. Its surface is struck by small objects, and each strike removes a little material. Some grains escape, others resettle. Over time, the escaping fraction feeds the outer ring. The ring is therefore not a fixed ancient object left unchanged since Saturn's formation. It is maintained by ongoing impacts, a quiet exchange between a dark moon and the space around it. The ring's tilt is another clue. Saturn's main rings lie close to the planet's equatorial plane, the flat plane associated with Saturn's rotation and the regular moon system. Phoebe's orbit is tilted relative to that plane, and the outer dust ring follows that tilted path. Its geometry points back to its source. The ring does not belong to the bright central architecture of Saturn. It belongs to the captured moon, to the irregular outer system, to the group of objects that came from elsewhere. This makes Saturn less simple than the famous image suggests. The bright rings give an impression of order, flatness, symmetry, clean divisions. The Phoebe ring reveals a second, dimmer order placed at an angle to the first. One ring system is visible, icy, close, and bright. The other is invisible to ordinary sight, dusty, distant, and dark. Both are real. Both belong to Saturn, but they tell different histories. The main rings may be young compared with the planet, though their exact age remains debated. Their particles are mostly water ice, bright enough to reflect sunlight strongly. They are sculpted by small moons, resonances, and collisions. They form a structure that can be mapped in detail, down to waves created by gravitational tugs. Phoebe's ring has none of that sharp detail from a distance. It is too spread out, too faint, too dark. Its beauty is not in fine edges. Its meaning is in reach. The reach is so large that if human eyes could see the ring from Earth, it would appear wider than the full moon. Yet it cannot be seen that way because its particles are too sparse and too dim. This is one of the strange lessons of astronomy. Something can be enormous and still hidden. Size alone does not make an object visible. Visibility depends on light, temperature, distance, contrast, and the patience of instruments tuned to the right signal. The same lesson appears again at the edge of the solar system, where the Oort cloud may contain countless icy bodies and still escape direct observation. A large structure can remain unseen if its pieces are small, dark, cold, and far apart. Phoebe's ring is closer and better tied to a known source, but it shares the same quiet character. It exists less as a picture than as evidence gathered from faint warmth and orbital logic. The particles in the ring do not stay forever. Solar radiation, Saturn's gravity, and small interactions slowly alter their paths. Some drift inward, some may be removed, some strike moons. The ring must be replenished if it is to remain present over long times. Phoebe, by enduring impact after impact, supplies that replenishment. A moon only a few hundred kilometers wide feeds the largest ring in the solar system. There is a softness in that scale reversal. The source is small, the result is wide. A single dark body, barely visible in many telescopes, creates a structure larger than all the bright rings combined. It does so without forceful display. No flare announces it. No plume rises like those of Enceladus. No volcano spreads fresh material across a moon's surface. Only impacts, dust, and time. The dust also connects separate regions of Saturn's system. Phoebe orbits far out. Iapetus lies closer in. The main rings lie closer still. Material from one region migrates into another, carrying color and chemistry across distance. A captured moon from the outer solar system affects the appearance of a regular moon that has orbited Saturn for ages. The system is therefore not a set of isolated objects. It is a web of slow exchanges, some obvious, some too faint to notice until instruments look in the right way. This exchange changes how a moon can be read. Iapetus's dark side is not only a property of Iapetus, it is a record of Phoebe. Phoebe's dust is not only material leaving Phoebe, it is a message moving inward. The outer ring is not only a ring, it is the path taken by that message, thinly written through space. In the silence between Saturn and Phoebe, the ring particles follow their own small orbits. A grain may be no larger than smoke or fine ash. It has no geology of its own, no world to preserve, no horizon. Yet it belongs to a planetary story. It was once part of Phoebe's surface. It may have been buried under dark material, struck loose by an impact, lifted away, and set into a path around Saturn. Later, it may meet Iapetus and become part of another moon's face. The grain's journey is small in mass but large in distance. The idea of a ring often suggests something circular, visible, and clean. Phoebe's ring is closer to a whisper of material. Its edges are not hard. Its density fades. It is better imagined as a tilted volume, a dark region of sparse dust through which moons move on their own paths. From inside it, there may be no clear sign of being inside anything. The stars would remain sharp, Saturn would remain distant, the dust would be too thin for a veil. Only careful measurement would reveal the place. This is why infrared astronomy matters. The universe does not show itself only in visible light. Cold dust, warm planets, young stars hidden in clouds, distant galaxies reddened by expansion, all can appear more clearly when instruments look beyond what eyes can see. Spitzer was built for that kind of seeing. In Phoebe's ring, it found a structure too cold and too dim for ordinary light, but not too cold to leave a thermal trace. The trace was faint because the particles are cold. They absorb sunlight and re-radiate a little energy as infrared emission. The signal is spread out, and it has to be separated from other background sources. Discovery required knowing where to look, how to interpret the glow, and how to match the geometry with Phoebe's orbit. The ring became visible not as a photograph in the usual sense, but as a pattern in the right kind of light. That pattern completed a circle of understanding. Phoebe's retrograde orbit explained why its dust would meet Iapetus head-on. Iapetus's dark leading hemisphere pointed back toward incoming material. The ring's tilt matched Phoebe's path. The dust's darkness matched Phoebe's surface. The pieces fit without needing an artificial cause. Saturn's outer system had been carrying the answer in plain motion for a very long time. The discovery also gives Phoebe a second identity. It is not only a captured moon, it is a source. It shapes the environment around Saturn beyond its own body. Its influence is not gravitational in the grand sense. Phoebe is too small to dominate the system. Its influence is material. It gives Saturn a hidden ring and gives Iapetus a darkened face. A moon can matter by what it loses. That loss is not tragic. It is ordinary planetary weather in a place without air. Surfaces are struck, dust is lifted, radiation alters grains, gravity sorts paths. The ring is made by the same slow physical habits that shape many airless bodies. Phoebe's difference is that the escaping material has enough space to spread into something immense. Saturn, seen from within the Phoebe ring, would be a distant center with a known pull. The bright inner rings would sit close to it, too far away to show their full detail without instruments. Iapetus would move through its long path, one face leading. Phoebe would continue farther out, dark and scarred. The ring itself would be almost nothing to the eye. And yet the whole region would be connected by dust. In that connection, the earlier theme returns. Bodies in space do not remain separate simply because distance lies between them. A planet pulls on a star. A moon pulls on a planet. A captured object paints another moon. A grain, leaving one surface, becomes part of another. The architecture of a system is not only made from orbits, it is also made from traces. The main rings of Saturn draw attention because they shine. Phoebe's ring asks for a different kind of attention. It is a structure of low light and long time. It shows that the largest things are not always the brightest, and that a faint signal may hold the missing explanation for an old mystery. The dark side of Iapetus, noticed centuries before spacecraft and infrared telescopes, was waiting for a ring no one could see. Now the path is clearer. Phoebe moves backward. Dust leaves its surface. The dust spreads into a tilted halo. Iapetus moves forward. Its leading face gathers the grains. Sunlight warms the darkened side. Ice migrates away. The contrast grows. A puzzle from the 17th century becomes a story of impacts. Infrared light, and a moon from somewhere beyond Saturn's original family. Still, the ring remains almost invisible. It does not become less real because it is faint. It circles in darkness, broad and thin, a quiet sign that Saturn's system extends far beyond the bright rings in every familiar image. Out there, the captured moon continues to shed dust into space, and the largest ring waits in the cold, seen only by the warmth of grains too small to cast a shadow. Beyond the orbit of Neptune, beyond the scattered bodies of the Kuiper belt, the solar system begins to lose its familiar shape. The planets no longer mark distance in any useful emotional sense. The sun is still the center, still the source of gravity and light, but it no longer dominates the sky the way it does from Earth. Farther out, sunlight thins until it is less like daylight and more like a cold memory of daylight, a faint pressure crossing enormous darkness. Somewhere in that darkness may begin the Oort cloud. It has never been photographed as a cloud. No telescope has seen its full outline. No spacecraft has entered it. It is not a glowing shell, not a mist that could be pictured from the outside, not a wall at the edge of the solar system. It is a vast reservoir of icy bodies, separated by distances so large that each object would move almost alone, held weakly by the sun across a depth of space that reaches toward nearby stars. The idea exists because of comets. A comet can appear suddenly in the inner solar system, brightening as sunlight warms its frozen surface and releases gas and dust. Some comets return on short, predictable schedules. Their paths are linked to the region beyond Neptune, where icy bodies orbit in the Kuiper belt and scattered disk. Others are different. Long-period comets may take thousands, millions, or even tens of millions of years to complete one orbit. They do not arrive neatly along the flat plane where the planets travel. They can come from steep angles, from directions above or below the solar system's usual disk, as if they were falling inward from a surrounding sphere. That pattern led Jan Ort to a quiet but far-reaching proposal in the middle of the 20th century. Long-period comets were not arriving from deep interstellar space at random. Their orbits still seemed bound to the Sun. They had been stored somewhere far away, far beyond the known planets, in a region where a small nudge could send one inward on a long falling path. The region was not observed directly, it was inferred from motion. The comets were the messengers, their paths pointed back to a hidden source. This is a different kind of seeing. A planet can be seen by reflected light. A ring can be seen by brightness or warmth. A star announces itself by fire. The Oort cloud offers almost nothing so direct. Its bodies are small by astronomical standards, dark, cold, and extremely far from the Sun. They do not shine. They barely reflect. Most have never entered the inner solar system, and most may never do so. The cloud is therefore known the way a distant shoreline might be known from pieces of driftwood arriving across a dark sea. The structure is usually imagined in two parts. The inner region may be more flattened, perhaps a thick disk or torus of icy bodies beginning thousands of astronomical units from the Sun. The outer region may be closer to spherical, extending so far that the gravity of passing stars and the Milky Way itself begins to matter. The boundary is not sharp. It is not like crossing a line from one country to another. It is more like moving outward through thinning influence, from the region where the Sun rules strongly to the region where the galaxy begins to share the steering. 1 astronomical unit is the average distance from Earth to the Sun. Neptune orbits around 30 astronomical units from the Sun. The Kuiper belt begins near that distance and spreads outward. The Oort cloud, by contrast, may begin thousands of astronomical units away and stretch to tens of thousands more. At those distances, the Sun is still massive enough to hold small bodies in orbit, but its light is weak beyond ordinary imagination. The Sun would not blaze. It would be a bright star, among other stars, stronger than the rest, but no longer filling the sky with warmth. Distance changes the meaning of time. Voyager 1 and Voyager 2 have crossed beyond the heliosphere, the bubble carved by the solar wind, and entered interstellar space in the sense that the particles around them are no longer dominated by the Sun's outward flow. Yet this does not mean they have left the solar system in the gravitational sense. The inner edge of the Oort cloud lies far beyond them. At their present speeds, a spacecraft would need centuries to reach its inner regions and many thousands of years to pass through the wider cloud. Human machines have touched the space between stars before reaching the distant storehouse of the Sun's comets. The heliosphere itself is only the Sun's atmosphere stretched outward into space, a bubble of charged particles flowing from the solar surface until the interstellar medium pushes back. Crossing it is a real boundary, but not the final boundary of the Sun. Gravity reaches farther than wind. A comet in the Oort cloud may receive almost no warmth from the Sun, may never feel the solar wind in any strong way, and may still be bound to the solar system by gravity. The solar system has more than one edge, depending on what kind of influence is being measured. This makes the Oort cloud a place of definitions as much as objects. The planets define one familiar system. The heliosphere defines the reach of the solar wind. The Oort cloud may define the farthest reach of the Sun's long gravitational memory. Beyond it, small bodies would be easier for passing stars or the galaxy to take away. Inside it, they remain, at least loosely, part of the Sun's family. The bodies themselves are likely ancient planetesimals, During the birth of the solar system, the giant planets grew in a disk filled with leftover icy and rocky material. Jupiter, Saturn, Uranus, and Neptune did not simply sit inside that debris. Their gravity scattered it. Some small bodies were thrown inward toward the sun. Some collided with planets or moons. Some were ejected entirely into interstellar space. Others were sent into enormous stretched orbits, far from the planets, but still bound to the sun. Over time, outside influences softened and reshaped those orbits into a distant reservoir. The outer planets were especially powerful in this early scattering. A small icy body passing near Jupiter could gain speed and leave the solar system. Passing near Neptune or Uranus, it might be moved into a wide orbit instead, one that took it far enough away for the galaxy's tidal pull or a passing star to alter its direction. In this way, material that formed near the young planets could be lifted into the outer darkness and stored there for billions of years. The word stored is useful but imperfect. The cloud is not still. Its bodies orbit slowly. Their paths are long ellipses, tilted in many directions. Over immense timescales, the gravity of the Milky Way pulls on them. Passing stars give small tugs. Molecular clouds may disturb parts of the reservoir. Most nudges are gentle. A body may shift slightly and continue its long path. Sometimes the change is enough to lower the object's closest approach to the sun. Then the ancient ice begins a journey inward. For most of its life, a long-period comet is not the bright object seen from Earth. It is a dark, frozen body moving far from sunlight. Its surface is hard with cold. Volatile ices remain locked in place. Dust lies mixed with frozen gases and rock. Nothing trails behind it. The comet becomes a comet in the familiar visual sense only when it approaches the inner solar system and the sun begins to warm it. Gas escapes, dust lifts, a coma forms, a tail stretches away under sunlight and the solar wind. The spectacle near Earth is a late event in a much longer orbit. A body from the Oort cloud may have spent almost the entire age of the solar system in darkness before making its first close passage near the sun. That possibility gives long-period comets their value. They can carry primitive material, altered less by heat than objects that have repeatedly passed near the sun. Each one is a sample from the cold outskirts, though not a sample held in a laboratory, unless a mission can reach or return material from it. Most are studied by light, gas, dust, and motion. The cloud also explains why long-period comets arrive from so many angles. The planets share a flat plane because they formed from a disk. The Kuiper belt also keeps much of that flattened structure, though the scattered disk is more excited and tilted. A spherical reservoir would send comets inward from any direction. Some paths dive from above the planetary plane, others rise from below. Their inclinations make sense if their source surrounds the solar system rather than lying only in the same flat region as the planets. The evidence is indirect, and that must be kept clear. The Oort cloud remains a model supported by comet orbits, dynamical simulations, and the physics of solar system formation. It has not been directly imaged. The honest answer is that astronomers infer it because the pattern of long-period comets asks for a source like it. Other explanations exist for some individual objects. Interstellar comets can pass through the solar system from outside, as Borisov did, but the broader population of long-period comets fits naturally with a distant-bound reservoir. Interstellar objects add a useful contrast. When an object comes from outside the sun's control, its orbit is not a closed path around the sun. It arrives with enough speed to pass through and leave again. Borisov, discovered in 2019, showed that comets from other star systems can enter the inner solar system for a brief visit. Its chemistry appeared different from many local comets, hinting at another birth environment. Such objects are real. They do not remove the need for the Oort cloud. They show that the space between stars also carries debris. There may even be Oort clouds around other stars. If planetary systems form with giant planets and leftover icy bodies, scattering should not be unique to the Sun. Other stars may be surrounded by their own distant reservoirs, too faint to see from across interstellar distance. Over long times, passing stars could exchange some of this material. A comet now bound loosely to one star might once have belonged to another. The galaxy may contain a slow traffic of icy bodies at the outer edges of stellar gravity. This makes the Oort cloud feel less like a final border and more like a porous shore. The Sun holds its distant objects weakly. Nearby stars pass, not often close enough to tear the system apart, but close enough over billions of years to stir the outermost region. The Milky Way's tide gently changes orbits. The edge is alive with small changes, not because it is crowded, but because it is so lightly held. Scholz's star gives one measured example of a close passage. Around 70,000 years ago, this low-mass binary system passed near the outer region of the Oort cloud. It did not send a storm of comets into the inner solar system. It was too low in mass, and the encounter too limited for that kind of disturbance. But simulations suggest it may have nudged some distant bodies. The visit is a reminder that the Sun does not travel through the galaxy alone. Other stars pass through its wider neighborhood, and their gravity touches the outer cloud. The effect of such passages depends on mass, distance, speed, and direction. A massive star passing close would have a stronger influence. A slow encounter would allow gravity more time to work. A dense molecular cloud could disturb many distant objects. Over the life of the Sun, many such influences have occurred, most now lost from direct memory. The Oort cloud may preserve some of that history in the distribution of comet orbits, though reading it is difficult. The cloud is also sparse beyond ordinary intuition. It may contain billions or trillions of icy bodies, yet the volume is so vast that neighboring objects would be separated by enormous distances. Standing on one, if standing were possible, no nearby world would be visible as a disk. The next body might be millions of kilometers away, or far more. The word cloud can mislead because it suggests mist or closeness. This is a cloud only in the statistical sense. Many small objects spread through a huge region. That sparseness helps explain why direct observation is so hard. An object the size of a mountain, sitting thousands of astronomical units from the Sun, reflects almost no sunlight back toward Earth. It is small, dark, cold, and lost against a field of stars. Even modern telescopes that can see distant galaxies are not automatically able to see such bodies, because galaxies shine with the light of billions of stars. Oort cloud objects do not shine. They hide in reflected light too weak to separate from the background. Future surveys may find more objects on extremely distant orbits, perhaps pieces of the inner Oort region or the extended scattered disk. Sedna already suggests that the outer solar system has structures beyond the classic Kuiper belt, with a detached path that never comes close enough to Neptune for a simple explanation. Such discoveries do not give a photograph of the cloud, but they add points to a map still mostly blank. The cloud's origin may also connect back to the Sun's birth environment. The Sun likely formed in a cluster with other young stars nearby. In such a place, close stellar passages were more common than they are now in the Sun's quieter galactic neighborhood. Those early encounters could have helped shape the outer reservoir, lifting or detaching orbits before the Sun drifted away from its siblings. If so, the Oort cloud is not only a result of the planets, it is also a fossil of the Sun's lost birthplace. That thought gives the distant cloud a deeper silence. It may contain objects scattered by Jupiter and Neptune, altered by the galaxy, touched by passing stars, and preserved from the time before the Sun became isolated. The bodies are small, but the history around them is wide. A single comet falling inward may have crossed influences from planets, stars, and the Milky Way itself before its ice ever brightened near the Sun. Near Earth, a comet can look delicate, almost fragile. A glowing head, a tail spread across the dark, sometimes visible for nights before fading. Yet the orbit behind that appearance may be immense. The comet may have traveled from a distance where the Sun is only a bright point. It may have spent millions of years returning. It may not come back for longer than human civilization has existed, or it may be on its first and last inward fall if planets alter its path. Jupiter often decides what happens next. As long-period comets pass through the planetary region, the giant planet's gravity can reshape their orbits. Some are thrown into shorter paths. Some are ejected from the solar system. Some fall closer to the Sun and break apart. Some survive and return to the distant cloud. The inner solar system is not a passive stage for comets. It is another gravitational crossing, and the largest planet is the strongest gatekeeper. The Oort cloud, then, is connected to the rest of the journey. It is made by scattering, like the paths that may have captured Phoebe. It is shaped by barycenters and gravitational relationships, like binary stars and circumbinary planets. It is nearly invisible, like Phoebe's ring, but revealed through traces. It shows that the solar system is not only the bright region of planets, it includes a dim outer memory, a place where ancient ice waits on orbits so long they feel almost still. Nothing there is truly still. The bodies move, the Sun moves, nearby stars move. The Milky Way turns. Over enough time, the faintest tug can matter. An icy body that has remained in darkness for billions of years can be shifted onto a path toward the inner planets. It begins as an unseen point in a distant reservoir. It ends, for a while, as a glowing visitor in the night sky. The cloud no telescope has seen remains one of the quietest structures associated with the Sun. It is enormous and almost empty, ancient and barely touched. Inferred but not photographed, its existence is not a claim of spectacle. It is a patient conclusion drawn from the way comets arrive, from how planets scatter debris, and from how gravity works at the edge of a star's reach. Far out there, the Sun still holds what it once threw away. Uranus moves in the outer dark with a posture unlike any other planet in the solar system. It does not stand upright in the familiar way. It rolls. Its axis lies so far over that the planet seems to carry its poles into sunlight and shadow like slow lanterns turning on their sides. From far away, it looks calm, blue-green, and almost featureless. A quiet sphere moving through the cold beyond Saturn. But that calm appearance is partly an accident of timing, partly an accident of distance, and partly the limit of the one close visit ever made by a spacecraft. Voyager 2 reached Uranus in 1986. The encounter was brief, fast, and precious. No spacecraft had ever been there before, and none has returned since. As Voyager 2 passed, it saw a planet in a strange seasonal position. One pole was aimed toward the Sun, while the equatorial regions received light at a lower angle. The planet did not show the bright bands and storms that made Jupiter and Saturn so visually rich. In the images sent home, Uranus looked muted, nearly blank, a pale, cold world, with only a few visible markings. For many years, that image shaped the planet's reputation. Uranus seemed quiet. It seemed plain. It seemed almost asleep. But later observations showed that this was not the full planet. Hubble and large ground-based telescopes, looking at Uranus as it moved farther along its long orbit, began to see more activity. Bright clouds appeared. Storm features changed. Bands and atmospheric structures emerged in wavelengths that Voyager 2 could not fully explore. The planet had not been empty of weather. It had been seen during one particular season, from one brief angle, at one point in an 84-year journey around the Sun. This is the first correction Uranus asks for. A single flyby is not the same as knowing a world. It is a glimpse. It can transform astronomy, but it can also freeze a planet in the imagination at the season when the spacecraft happened to arrive. Uranus is not a still blue marble. It is an ice giant with long seasons, hidden winds, a strange magnetic field, dark rings, moons, and an interior that remains largely unknown. Its tilt is the most visible mystery. Earth leans by a little more than 23 degrees, enough to give the planet its seasons. Mars leans by a similar amount. Jupiter stands almost upright. Uranus is tilted by about 98 degrees, so far that its rotation is often described as sideways. During part of its orbit, one pole faces the Sun for decades, while the other remains in darkness. Later, as the planet continues around the Sun, the equator receives more balanced light. Then the opposite pole takes its long turn under the Sun. A season on Uranus is not a few months. It lasts for roughly 21 Earth years. A child born at one solstice on Uranus would reach adulthood before the season changed to the next major stage. A polar region can remain in sunlight for longer than many human lives have existed in memory, then pass into darkness for a similarly long span. The idea of summer and winter becomes slow enough to feel geological, though it is only orbital mechanics stretched across a distant path. The cause of the tilt is still debated. The simplest picture is a giant impact early in the planet's history, when a large body struck Uranus and rolled it onto its side. But one impact has to explain more than the tilt. It must also fit the planet's moons, rings, rotation, and internal structure. Some models suggest more than one impact. Others explore whether gravitational interactions during the early migration of the planets might have helped alter the spin. The answer is not settled. What is clear is that Uranus carries a memory of a violent early event or sequence of events, now expressed as quiet, sideways rotation in the present. The moons of Uranus follow its tilted equatorial plane. That matters. If the planet had been struck after its moons formed in their present arrangement, the system might look different. The fact that the moons orbit in the tilted plane suggests that the event, or the reshaping after the event, happened early enough for the satellite system to settle into that sideways geometry. The rings share the same strange orientation. The entire inner Uranian system seems to have accepted the tilt as its reference frame. From the point of view of the Sun, this creates a planet where light moves across the atmosphere in a pattern unlike any other giant planet. A pole can sit under continuous weak sunlight. The opposite pole can wait in darkness. The equator can pass through periods of changing illumination as Uranus reaches equinox, when sunlight falls more evenly across both hemispheres. Weather under such conditions should not be simple. It may respond slowly because the atmosphere is massive, cold, and far from the Sun, but it still responds. The atmosphere is mostly hydrogen and helium, with methane giving Uranus much of its blue-green color. Methane absorbs red light and allows bluer light to scatter back into space. Beneath the visible cloud tops, pressures rise and temperatures change through layers that cannot be seen directly. Water, ammonia, and methane may exist in exotic high-pressure states deeper inside. The phrase ice giant does not mean a frozen solid planet. It means a world rich in heavier volatile compounds compared with Jupiter and Saturn, wrapped in gas and shaped by internal conditions no surface observer could stand upon. There is no solid ground visible from above. A probe descending into Uranus would fall through cloud layers, gas, haze, and pressure, with no clean boundary where atmosphere becomes surface. The deeper it went, the more ordinary words would fail. Ice, liquid, gas, and fluid become less useful distinctions under the pressures inside an ice giant. Materials behave according to conditions that cannot be reproduced easily at full planetary scale on Earth. Uranus is therefore not only far away, it is physically unfamiliar. Its internal heat is another puzzle. Neptune, similar in size and composition, radiates much more internal heat than it receives from the Sun. Uranus radiates surprisingly little. It seems colder inside, or at least less willing to release heat outward. This difference is not fully explained. Perhaps the impact that tilted Uranus changed the way heat moves through its interior. Perhaps the planet has layers that prevent convection, trapping warmth deep below. Perhaps its formation history differed from Neptune's, in ways still hidden. The planet's bland appearance in visible light may be connected to a deeper quietness inside. The magnetic field is stranger still. Earth's magnetic field is tilted only modestly from its rotation axis and is generated deep inside the planet. Uranus has a magnetic field tilted strongly away from its rotation axis and shifted away from the planet's center. Neptune has a similarly unusual magnetic geometry. These fields may be generated not in a central metallic core, but in a shell of electrically conducting fluids at shallower depths. If so, ice giants operate differently from rocky planets and gas giants. Their magnetospheres are lopsided, changing dramatically as the planets rotate. Around Uranus, that means the magnetic environment is not a simple bubble aligned with the planet's spin. It tumbles and twists as the sideways planet rotates, exposing moons and rings to a changing field. Charged particles move through this tilted magnetic space. Auroras can appear far from where Earth-based intuition might place them. The whole magnetosphere is a rotating, uneven structure, a reminder that a planet's invisible fields can be as distinctive as its visible clouds. The rings of Uranus are dark and narrow, discovered from Earth when the planet passed in front of a star, and the starlight blinked before and after the planet itself crossed it. They do not shine like Saturn's bright rings. They are thin, charcoal-dark arcs of material, likely made of radiation-darkened particles and fragments. Voyager 2 imaged them more clearly, but they remain faint, quiet features. Like Phoebe's ring, they show that not all rings announce themselves in brightness. The moons add another layer. Uranus has 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Their names come not from classical mythology in the usual planetary pattern, but largely from Shakespeare and Alexander Pope. They are icy, rocky bodies, each with its own history of impacts, fractures, and possible internal change. Miranda, especially, appears fractured and reassembled, with enormous cliffs and strange terrain that suggest intense past disruption or internal resurfacing. Around the tilted planet, these moons move in sideways orbits, sharing the planet's unusual plane. Voyager 2 saw only one hemisphere of many Uranian moons in detail, because the lighting and flyby geometry allowed no complete survey. Half-known worlds remain half-hidden. The unseen sides may carry craters, fractures, planes, or signs of history that no camera has yet mapped at high resolution. In the outer solar system, ignorance often has a simple reason. The object is too far away, and the spacecraft has passed only once. That is why Uranus has returned to the front of planetary science planning. The National Academy's Planetary Science Decadal Survey identified a Uranus orbiter and probe as a top priority for a future flagship mission. Such a mission would not merely fly past. It would orbit the planet, watch the atmosphere change through time, map the magnetic field, study the rings and moons, and send a probe down through the atmosphere to measure composition, temperature, pressure, and winds directly. The difference between a flyby and an orbiter is the difference between a glance and a long stay. An orbiter could see seasons change, though even a mission lasting years would observe only part of a Uranian season. It could watch storms form and fade, It could map the gravity field and infer interior structure. It could measure how heat escapes, or fails to escape, from the depths. It could examine whether some moons may have had internal oceans in the past, or perhaps retain layers of liquid water deep inside. None of this needs exaggeration. The science is already rich because the planet is so poorly known. Uranus also matters beyond the solar system. Many exoplanets discovered around other stars fall into size ranges between Earth and Neptune. Some may be mini-Neptunes, some may be water-rich worlds, some may be rocky planets with thick envelopes, and some may resemble ice giants in broad composition. The solar system has only two ice giants, Uranus and Neptune, and both are distant, underexplored, and different from each other. To understand the many medium-sized planets in the galaxy, the nearest examples need to be understood first. This is a quiet reversal. Uranus is sometimes treated as a remote oddity, but it may be one of the most useful planets for interpreting worlds around other stars. Its cold atmosphere, unusual heat balance, tilted magnetic field, and sideways seasons are not isolated curiosities. They are pieces of a larger question. How planets in this mass range form, cool, organize their interiors, and hold their atmospheres over billions of years. The journey that began with shared centers of mass now widens again. Uranus, like every planet, does not move around a perfectly fixed sun. The sun itself shifts around the solar system barycenter as Jupiter and the other planets pull on it. The planets tug on one another. Comets at the edge of the Oort cloud feel the galaxy. Phoebe carries the memory of capture. Circumbinary planets move under two suns. The same rule keeps returning in different forms. Nothing is isolated. Even the sun is not still within the Milky Way. It moves around the galactic center with the rest of the local stellar neighborhood, carrying the planets, moons, rings, asteroids, Kuiper belt, and distant comet cloud along with it. Nearby stars have their own motions. Over millions of years, the sky changes. Constellations stretch and dissolve. Stars that seem fixed drift apart or draw closer in projection. The night sky is a temporary pattern seen from one moment in the galaxy's long turning. Gaia has made that motion visible with new precision. By measuring positions, distances, and proper motions for enormous numbers of stars, it has turned the Milky Way from a flat band of light into a moving map. Stars near the sun are not painted onto a background. They have paths. Some belong to streams. Some move with clusters that slowly loosen over time. Some carry traces of past encounters between the Milky Way and smaller galaxies. The galaxy is not a still stage. It is a structure in motion, layered with histories. This zoom outward does not make the smaller worlds less important. It gives them context. A grain of dust from Phoebe, a comet in the Oort cloud, a tilted ice giant, a planet under two suns, and a star moving through the Milky Way all belong to the same universe of motion. The scales differ, but the principle remains. Gravity writes curves. Time lets those curves become histories. Uranus turns on its side under weak sunlight. Its clouds shift slowly. Its rings circle in darkness. Its moons follow the tilted plane around it. Farther out, the Oort cloud waits in near invisible distance. Farther still, other stars move through the galaxy. Some alone, some paired, some with planets of their own. The solar system travels among them, not as a fixed island, but as one moving family inside a larger current. There is a calmness in this, not because the universe is simple, but because its motions are patient. A planet may be knocked sideways and still continue for billions of years. A moon may be captured and become part of a new system. Dust may leave one body and alter another. A comet may wait in darkness before falling inward. a pair of stars may turn around an empty center, while planets keep to the safe outer path. The universe does not need stillness to endure. The old drawing of a star at the center with planets on neat rings remains useful for a first glance. But the deeper picture is softer and more alive. Centers shift, orbits lean, systems borrow objects from their past. Boundaries blur. Light hides some structures and reveals others. A planet that once looked blank becomes a world with seasons too long for a single human life to witness. A distant cloud that no telescope has seen becomes the source of comets that brighten near Earth. A dark moon becomes the maker of a ring. At the end of the outward path, the feeling is not that the solar system is stranger than expected. It is that strangeness is part of its order. The planets are not arranged by accident, yet their arrangement was not inevitable. They formed, migrated, scattered, captured, tilted, and settled. What remains today is a system still moving, still changing, still carrying signs of earlier chapters in every orbit. Uranus continues around the Sun, slowly rolling through its long year. Another season passes over one pole. Another darkness gathers over the other. No spacecraft is there yet to watch every change. From Earth, telescopes keep returning to the pale distant disk, looking for clouds, storms, rings, and hints of the interior below. The planet waits without hurry, and the Sun moves with it. The whole system drifts through the Milky Way, carrying its tilted worlds, captured moons, hidden rings, and unseen cloud of ancient ice. Around it, the nearby stars also move, each with its own balance, its own companions or solitude, its own possible worlds. Nothing holds perfectly still. Nothing truly travels alone. The journey now begins to slow. The distant stars remain where they are for this quiet moment, scattered across the dark like small points of memory, while the great motions continue without needing to be watched. Binary suns keep turning around their unseen centers. Cold planets follow the curves that hold them. Saturn's far outer moon moves through its backward orbit, dark and patient, still releasing dust too faint for ordinary sight. Beyond the planets, the ancient cloud of ice waits in the distance, almost motionless to the mind, though every piece of it is still traveling. There is no need to follow every orbit now. The details can soften. The names can drift away. What remains is the feeling of space opening wider and wider, then becoming gentle again, no longer asking for attention. The Sun is only one star among many. The solar system is only one moving family in the galaxy. And still, within all that motion, there is balance enough for worlds to remain, for moons to keep returning, for dust to cross darkness, for faint light to arrive after years of travel. The room is here again. The air is still. The body can rest while the universe continues outside the window, turning slowly beyond sight. Nothing has to be held in place. Nothing has to be solved. The stars will keep their long paths. The planets will keep their silent years. Far away, Uranus rolls through its season. Phoebe circles Saturn, and the hidden edge of the solar system waits in the cold. The thought can fade now, like starlight thinning into sleep. Motion continues. Darkness deepens. Everything is held, softly, by gravity and time.